So in this problem, we're given a situation that looks like this. We have a rock of mass m that's being twirled in uniform circular motion in gravity-free space about the y-axis. It's being twirled at a distance d, and it's moving at a linear velocity v. So in part A, we're asked what the direction and magnitude of the angular momentum vector is going to be. We know that angular momentum is equal to r cross p, so we're going to actually solve this in two steps. First, we're going to find the magnitude of r cross p, and then we're going to use the right-hand rule to find the direction. So r cross p, the magnitude of that is going to be the magnitude of r times the magnitude of p times the sine of the angle between them. R is equal to, the magnitude of r is equal to d. The magnitude of p is equal to mv. So the magnitude of this is d mv sine theta. The two of them are at right angles, and we know that the sine of 90 degrees is equal to 1, so we don't have to worry about that term. Now the direction of the angular momentum vector, we're going to use the right-hand rule. We know that d is pointing straight this way, and the velocity is pointing straight across here, around clockwise around this circle. And so that tells us that by the right-hand rule, the cross product of them is going to point in the negative y-hat direction. It's a little bit hard to see because it looks like my thumb is pointing inwards to the board, but that's kind of confusing because this is a three-dimensional diagram. So if you pictured this with the y-hat component actually pointing straight up and this circle moving around here, we've got d here, and the velocity is in this direction. And so that tells us that the angular momentum vector is pointing downwards, as you can see. Now in part B, we're asked that if the string were to break, what would the subsequent angular momentum of the rock be? And in fact, the rock would simply maintain the same angular momentum. Something that is suddenly released from circular motion, as long as no torques act upon it, angular momentum will be conserved, and so it won't, the angular momentum of it will not change in magnitude or in direction. And in this case, it kind of makes sense. So if the rock were suddenly to stop moving in a circle, it would maintain the same momentum, but it would just point off and continue to go along in that direction. So say it were at this point, it would have the same momentum vector, but r would be all the way down here. So it seems a little bit weird that r cross p would be the same for both of these sets, but in fact, remember that the magnitude is going to be r times p times the sine of the angle between them. And if you move the sine theta over so that you get r sine theta times p, r sine theta is just exactly this perpendicular component right here. And then, of course, the right-hand rule is going to continue to give us the same direction so long as this angle is less than 180 degrees, which it will, so it will remain so long as the rock continues to move in this straight line. And so both the magnitude and the direction of the angular momentum vector will stay indefinitely the same until some other force acts upon the rock.